Hello everyone, welcome to lecture 2 of Alkanes. Okay, for this lecture, we're going to talk about the reactions of alkanes, talk more on the free radical substitution mechanism, which is the focus of this lecture. And on top of that, we're going to talk about some environmental consequences for the use of alkane, catalysts to remove exhaust gas, as well as the enhanced greenhouse effect. So for a start, let's look at some of the reactions of alkanes. So alkanes itself basically undergo three main types of reaction. The first one is the combustion, followed by your free radical substitution. So for the first one we're going to talk about is combustion. I think everybody knows what is combustion. And alkanes, because it's a hydrocarbon, when I combust it in excess oxygen, I actually get my carbon dioxide and my water only. And this reaction is highly exothermic, given by this equation. I think this equation is not strange to you, it's not foreign to you. You have seen this before in your atoms, molecules, and stoichiometry when we are doing the idiometry part of that topic. So it's a hydrocarbon burned in excess oxygen, complete combustion, giving rise carbon dioxide and water. So these are some examples of the enthalpy change of combustion of some of the alkanes that are more commonly used, showing you how much energy they release per mole of alkane burn. Looking at checkpoint 5 now, we have to account for the trend observed in the magnitude of the enthalpy change of combustion from methane to butane. So you can refer to your lecture notes at the top, the table there, table 1.2, to see the different enthalpy change of combustion. So I give you 2 minutes to write down what you think before you check back at this video. Welcome back. So let's take a look at checkpoint 5. So for checkpoint 5, you are supposed to account for the trend. So like mentioned, you can actually look at the table on top and you'll find that the value or the magnitude of the enthalpy change of the combustion actually increases down the group when you change from methane all the way to butane. So like mentioned, the first observation you can say is that there is actually an increase in magnitude in the enthalpy change of combustion from the methane to the ethane, ethane to propane, and then propane to butane. So this is your observation. So the reason for it is because as it goes down the group from methane to butane, you notice that each successive alkane actually increase by a CH2 unit. So the difference in enthalpy change values are actually due to the combustion of additional CH2 units in each of them. Next, we're going to talk about free radical substitution as well as the mechanism for free radical substitution. So what is a free radical substitution? So basically, okay, it is given by you have alkanes. Okay, so the alkanes can undergo the free radical substitution with a halogen. So as seen by this equation, you have R, which is your alkyl group, and then your X is actually your halogen. So this is actually a photochemical reaction whereby you actually use the UV light first, okay, to start the reaction. So it actually provides the energy needed for the generation of the radicals. Okay, thereafter, then you have the substitution of the hydrogen atom by the halogen atom. So this is what you see in the overall equation. Okay, so like mentioned, you need your UV light and your strong heating for the generation of the free radical at first. Next, you might be asking me what are radicals, because probably the thing that you hear about radicals is probably free radicals, right? Okay, so in radicals itself, it's basically, okay, some species that possesses at least one unpaired electron. So what do I mean by an unpaired electron? That means not a lone electron lah. So like in this case, this is a unpaired electron. So this one here. And then for this one, same thing, you will have a unpaired electron. So we give it a dot, okay, to represent the radical. So fluorine here also have a unpaired electron. Okay, so in this case, in order for me to substitute the H with F, okay, it has to go through a substitution. So this type of reaction, we call it the free radical substitution. Before we go on to the mechanism mechanism that you see inside your notes, okay, there are a few things that would like to highlight to you first. Okay, a free radical, okay, substitution are using radicals. So the radicals are actually formed when I have a high heat or a light, okay, is present to cleave the bonds. Okay, so I would like to highlight to you that the bonds are actually cleaved homolytically to produce the radical. So let's say I have a A and a B. I cleave them, I get a A radical and a B radical. Okay, so if you notice the arrow that I draw, if you zoom in, you notice the arrow that I draw is actually a fish hook arrow or a half arrow. That means to say it is not full, it is only half. Okay, it's only half, so it is not a full arrow. So this is what we mean by the bonds cleave homolytically to produce the radical, meaning to say when the bond cleave, okay, you can say it very simply like the A takes back its electron, the B takes back its electron. Okay, so yeah, that's the meaning of it. So free radical substitution do not give only one product. Multiple substitution can occur. Oops, wrong. It's a pen. Ew. Okay. Okay, multiple substitution can occur, giving rise to a mixture of products. So that is my free radical substitution. So the amount of whether I want the amount of the mono substituted or the poly substituted, okay, will be influenced by the amount of the hydrocarbon and the halogen that you add in. So for example, in this case, if I want a large proportion of mono substituted, that means singly substituted, then I will need a large excess of what? I will need a large excess of hydrocarbon. Okay, because if your hydrocarbon is more than your halogen, right, then most of it will be mono substituted. On the reverse side, if you want your hydrocarbon or your alkane to be substituted with many Cl atoms, then of course I would naturally use an excess of the halogen. The reactivity of the halogen, okay, will also affect. So let's say for example, I have my F2, Cl2, Br2 and I2. Okay, we all know that our F2 is very explosive. Okay, so even in the dark or in the cold. And then for my Cl2 and my Br2, it will happen, okay, in the presence of UV light or heat. And the I2, there will be no reaction. So if you look at it in terms of the reactivity, you will notice that in FRS or the free radical substitution reaction that we're going to talk about, okay, we will be using mainly Cl2 and Br2, or I should say in many of the examples that you see will be Cl2 and Br2 because they can happen in the presence of UV light. Whereas I2 will nothing will happen, so we will not use it. And then your F2 is too explosive, so we will also not use it. So now I would like to introduce to you the mechanism for the free radical substitution. So before we go on to talk about it, the mechanism and what it entails, I would like to introduce the 3 steps to you first. The first step is actually your initiation, followed by your propagation, and finally your termination. So with these 3 steps, you can actually write an overall equation like this. Okay, but this overall equation doesn't tell you what happened in each step. So now let's take a look at each step. I'm currently at page 10 of your lecture notes. So you can actually follow and take a look. So for the initiation itself, initiation means to start, right? Start the reaction. So how am I going to start? Previously, you know that to start, I need to have a radical first. So in order for me to have a radical, I need to have UV light to start the reaction, to break the bonds. So when my Cl-Cl bond breaks, it will generate 2 Cl radical in the presence of UV light. Now, in mechanism itself, I would also like to highlight to everybody, the mechanism itself, we will need to draw arrows. So in this case, this is actually a half arrow. So you will notice that in the drawing itself, in the initiation, I actually put in the arrows to show my examiner that yes, I know that the bond actually break homolytically and each of the Cl actually takes back its own electron to form the radical. So one molecule will form 2 radicals. Next is the propagation step. So the propagation step is the step whereby you will get your product. You will need to form till you see your product that you want depending on the question. So in this case, in propagation, there is a step 1 and a step 2 of the propagation itself. So in step 1 of the propagation, just now from the initiation step, you already form your free radical. So this free radical will go on to react. So this radical will react with which species? The radical will react with your in this case is your ethane molecule. So you will have the radical reacting with your ethane molecule and one of the CH bond will break to form your ethyl radical and your HCl molecule. So like mentioned, it's not good enough just to show me the equation. You have to show me the arrows. So I show you the arrow. I show the breaking, I show the forming. So this is actually the formation. Can see that it forms, and this part here is actually the breaking. Okay, so you can actually see the breaking and the forming. So when I have one molecule plus one radical, I will form one radical and one molecule. So that is the step 1. So the step 2 means I need to form back. I need to show people the formation of the mono-substituted ethane, right? So then this radical will then react with who? The radical will now react with a molecule. So it will react with my Cl2 molecules to give me my chloroethane. So same thing, show your arrows. So also one radical plus one molecule, giving me one molecule and one radical. So that is your step 1 and your step 2. So the step 2 actually shows the formation of your chloroethane. So after the propagation step, we will move on to the termination. So in the termination, by the term means, right, terminate means what? Terminate means when the reaction stop lah, terminates, right? So how does it happen? How does the reaction stop? Because there are so many radicals coming around, right, floating around. So what is happening is that when 2 radicals meet each other, so when they meet each other, you will see them coming together and they form a bond. So when they form a bond, they actually form a molecule. So when 2 radicals form a molecule, the reaction stops because this is now a molecule and then it will terminate. So these are examples of the termination. So in the termination itself, you just need to show 2 of the termination will 2 steps will do. That means you just need to show how 2 radicals come together to form one. So let's say I can choose this one. Okay, I will usually like to choose the easy one. I will choose this one and this one. So I'll just show two steps, okay, or two reactions, okay, how it actually terminates. And that will be good enough for me because there are many possibilities to the termination. So I just show two of them and I show my examiner that I understand what is termination and then it's good enough. So the propagation, like mentioned, the propagation is the one whereby it gives you the product. So the propagation step can also give rise to a di-substituted, okay, or a tri-substituted products, depending on how much halogen that you put in. So for example, in this case, okay, this one can continue, okay, to give me a di-substituted product. Okay, so it is not possible, seriously, okay, to control where the radical is attacking. Okay, that is why in a free radical substitution, we often say that it always gives a mixture of products. So in a free radical substitution, it will give many different type of products, some major, some minor, depending on which one you put in more, which reactant you put in more. So that's why further down the road, okay, when you're going to learn more about the different homologous series, different types of organic compounds, and whereby you are asked to do synthesis itself or maybe distinguishing tests, okay, you will notice that we usually do not encourage our students to use free radical substitution because there is really too wild. The number of products that can come out is really too unpredictable. There's a mixture of products, so you will not get a high yield for that particular compound that you want to synthesize out. So that's why we usually do not recommend. Yep. So keep this in mind when you come into later part of the organic series. You will have more chance to see and synthesize certain products, and then you will understand why we usually don't use free radical substitution. Moving on next, this is actually on page 11 of your notes. At this moment, you will notice that it is actually in box up in the lecture notes itself. So probably you might be wondering, is this enrichment? Okay, now, this one is not specifically in the SIO as per se, but the problem is that you will need to know the stability of the hydrocarbon radical in order for you to attempt your questions. Okay, so since I'm here, I may as well give you a little bit of idea what is the stability of the hydrocarbon radical. So you notice that there is actually different types of radical. So given by the fact that there is a methyl radical all the way to a tertiary radical. So what is happening is that the stability of the methyl radical is the least stable, and then the tertiary radical is the most stable. So the reason for it is because this carbon here itself is actually electron deficient, right? Because it does not have the octet configuration. So because it is electron deficient, it is unstable. But if I have some methyl group, like for example, in this case, I have three methyl groups, okay, that is bonded to it, you know that the methyl group is weakly electron donating, so it actually helps to stabilize your radical. Okay, now the stability of the radical is actually in comparison. So when I say that my tertiary radical is more stable than my secondary radical, is actually in comparison between the two of them. Okay, so you can say that if I have more substituted the radical is, then I will say it is more stable. So that is the idea of the stability of the tertiary radical compared to the methyl radical. The next one that you see inside the box is actually the delocalization of the pi system, okay, such as benzene ring. I will not talk too much about this because you are actually going to learn this again in arenes, okay, but at this moment, I just raise awareness to you, okay, that if radical can also be stabilized by delocalization of the pi electron cloud in benzene ring. Okay, so yep, I will leave it to the lecturer who is teaching radicals, the benzene ring, the arenes, sorry, arenes to give you more insight of this concept of the delocalization.
We will now do a checkpoint. Pay attention to the details given in the questions. In part B, your mechanism must show two hydrogen atoms being substituted to form 1,1-dichloropropane. In part C, the suggested reaction conditions must give 1-chloropropane as the major product. Please pause the video now to try this checkpoint. Let's now go through the answer. The reagents and condition required is chlorine gas in the presence of UV at room temperature. To present your mechanism, you will need to label clearly the three stages: initiation, propagations, and terminations, and write balance equations for each elementary steps, and include the half arrows to show the movements of single electrons. So in the initiation stage, the Cl-Cl covalent bond undergo homolytic fission. Note the way half arrows are drawn. It shows each chlorine atom taking back its own electrons in the covalent bond to form chlorine-free radicals. In the propagation stage, we need two steps to substitute one hydrogen atom with chlorine. Relevant CH covalent bond must be shown clearly in propane molecule to ensure that the correct hydrogen is eventually substituted. In this case, we need to show the covalent bond between carbon 1 and its hydrogen. All half arrows must start from either the unpaired electrons or the covalent bond to be broken. When a new covalent bond is formed, the electrons must combine. This is represented by the two arrows meeting each other. This will give rise to the C-Cl bond. Notice there is a small half arrows that end on the carbon C. This accounts for the unpaired electrons on the carbon of the propyl radical. In the second step, the propyl radical intermediate will react with a chlorine molecule to form 1-chloropropane. You will have to draw your half arrow in the same way to show the movements of electrons. So the arrow must start from the free radical or the covalent bond that is to be broken. Two of the arrows will meet at somewhere, showing that these two electrons eventually forms the new covalent bond. So this gives rise to our CCl covalent bond in our product. Now this step will regenerate a chlorine radical for further reaction. To show the formation of a di-substituted product, we need a third and fourth step for the propagation. The third step involves the mono-substituted product from the previous step and the chlorine-free radical. We will have to show the half arrows starting from the chlorine radical and the CH bond. Two of the arrows must meet to show the electrons combining to form HCl covalent bond. Again, there is a small little arrow from the covalent bond to the carbon. This will give us the unpaired electron on carbon. In the fourth step, this is very similar to step 2, when chlorine molecule is involved in the reactions and a chlorine-free radical is regenerated. Likewise, for the half arrow, check that you have a half arrow starting from the radical and two other arrows starting from the Cl-Cl covalent bond. These two arrows will meet to show the electron combining to form this C-Cl covalent bond. In the terminal stage, choose any two radicals from the propagation steps to form a molecule. Note, the arrow must always start from the unpaired electron and meet somewhere. You will need to show a total of two terminal steps. I can also write this third equation as my terminal steps. There are also many other possible combinations of equations, but it is obvious why I would prefer the first two, as they are easier to write. In part C, for there to be a large excess of a mono-substituted product in the reaction mixture, I will need to limit the amount of chlorine used or use an excess of propane. This is because when I have less chlorine, less hydrogen atoms on my propane will get substituted.
Moving on to the next part is actually talking about environmental consequence for the use of alkane. I think you know that alkanes is actually used in fuels like your petrol, your diesel. So basically they are actually combusted, and because they are combusted, right, carbon dioxide will produce, but sometimes if it doesn't have a complete combustion, then you might have some pollutants that we do not want. So some of the pollutants, for example, is your carbon monoxide, your unburned hydrocarbon, or you might have some oxides of nitrogen. So all these are undesirable car exhaust that is happening inside the internal combustion engine. The next part of it is actually your catalytic remover of some selected exhaust gas. Okay, now in the previous part whereby I talk about the environmental consequence of the use of alkanes, right, there are actually some readings that I would like you to read on your own. For example, the pollutants in the car exhaust, the unburned hydrocarbon, and the oxides of the nitrogen itself. Please go and read on your own. So moving on to the next part whereby I have my catalytic removal of the selected exhaust gas. So basically this one is just telling you that I will put a catalyst inside the car or the machine, okay, to remove the harmful gases. So some examples of it is your platinum and your palladium, whereby I actually remove the unburned hydrocarbon, or I remove the carbon monoxide. Basically, in a catalytic remover, right, you are trying to produce a harmless gas, okay? Change from harmful to harmless. So this is a read up for you. A lot of it is actually, I'm not sure whether have you learned this before. Probably you did in geography. I think probably those who do geography, do you all learn this before maybe? Okay, so yep, you can read up on your own. Lastly is the enhanced greenhouse effect. The enhanced greenhouse effect talks about the various greenhouse gases that we have in our environment and how the sources actually where are they produced lah? Okay, how are they produced? All the different greenhouse gas. So I have a video here to show you the greenhouse gases effect.
Heat from the sun. It keeps us warm. It makes trees grow, giving us food. And it pretty much keeps everything alive and happy. But what happens to all that bright white energy after it reaches us here on Earth?
For me, they give you vitamin D, and for the tree, they help it stay alive. When they hit the ozone layer, part of it gets absorbed and part of it goes up into space.
It depends what's on the ground. Sometimes it reflects up into the air, and if you're standing on top, it might reflect onto you. But if it doesn't reflect, it just stays on the ground and it doesn't go anywhere.
In a way, they're all right. Some of the sun's hot rays are absorbed, warming up the planet. But a lot bounce back out into space. And on their way out, sometimes they get stuck. That's because they bump into tiny little particles floating in the atmosphere, called greenhouse gases. They include carbon dioxide, methane, and nitrous oxide.
It's normal for greenhouse gases to be up there in the atmosphere doing that. They're a natural part of Earth's climate system. In fact, without them, our planet's average temperature would drop to minus 18 degrees, meaning all the water on Earth would completely freeze over.
So in many ways, greenhouse gases are great. You can think of them as being like blankets on a cold night. They trap more heat in to keep us warm. But what happens if we put on too many? Things start to get hot. And the same thing could happen with our planet. Unfortunately, our main energy sources like coal and petrol release extra greenhouse gases into the atmosphere. So by generating energy like that, it's kind of like we're putting more blankets on the planet. In fact, scientists say, thanks mostly to humans, greenhouse gases have risen to their highest level in 800,000 years. And that could cause some big problems. Climate scientists say it'll warm up the planet, which will melt ice, causing sea levels to rise, and that will threaten people living close to the water, and some animals will suffer too. More greenhouse gases could also cause our intricately balanced climate to change, meaning more extreme weather in the future. Scientists say if we don't start to bring greenhouse gases down to natural levels, the damage will be severe and irreversible. So they're calling on the world's governments to find ways to reduce greenhouse gas emissions. Compared to the levels in the year 2000, the Australian government is trying to cut greenhouse gases by 5% within 6 years. That's going to be pretty hard, so they'll be giving big businesses money to try to invent new ways to tackle the problem. And they're building a green army of young people to plant more trees, because trees actually drink in one of the gases, carbon dioxide. But everyone needs to chip in, and that's not just other countries, it's also you and me.
The Australian Youth Climate Coalition's 3 top tips for reducing your greenhouse gas emissions are 1, to ride your bike to school, 2, to buy less stuff, and 3, to talk to your parents about climate change.
Given scientists want us to completely stop using energy sources like coal and petrol by the year 2100, it might be time to get a roll on.
So having watched the video that is on the greenhouse effect, so in summary, okay, it's actually whereby this is the natural greenhouse effect, okay, to keep us warm, but too much of it actually not good, okay, and that is where we have the global warming. Lastly, before I end off this video or this lecture, I would like to show you another case about the ozone, which is actually on the last page of your lecture notes. The one about the ozone, the formation and the destruction of the ozone in the stratosphere. Okay, so I think it's a good knowledge to have, and this video it tells you more about the ozone itself. So let's take a look at this video.
Earth, a beautiful blue marble. Who would guess that serious changes are taking place in its atmosphere? These visible wavelengths are only a part of the electromagnetic spectrum. What you don't see are the radio, infrared, gamma, X-rays, and the sun's harmful ultraviolet rays, known as UV. So how does ozone play a part in this story? Ozone is a relatively unstable molecule found in the 3 layers of the Earth's atmosphere. In the stratosphere, ozone acts like a warrior's shield, protecting us from the sun's ultraviolet radiation. With the depletion of ozone, we become more vulnerable to skin cancer and cataracts.
Ozone is O3. In other words, the ozone molecule is made up of 3 oxygen atoms. Ordinary oxygen is O2. High-energy ultraviolet radiation in the stratosphere breaks oxygen molecules apart, forming 2 separate oxygen atoms. These oxygen atoms are highly reactive, and they quickly join nearby oxygen molecules to form ozone. Stratospheric ozone protects us because it efficiently absorbs ultraviolet radiation. The absorbed UV energy splits ozone into an oxygen atom and an oxygen molecule. The free oxygen atom quickly combines with a nearby oxygen molecule to reform ozone. We see that ozone forms, breaks up, and forms again in a repeating process. Because of this continuous repeating process, UV is absorbed by ozone and less reaches Earth. Because ozone is a highly reactive molecule, it interacts readily with nitrogen, hydrogen, bromine, and chlorine compounds. For example, when a chlorine atom collides with an ozone molecule, it steals an oxygen atom to form chlorine monoxide, and it leaves behind an ordinary oxygen molecule. When a free atom of oxygen collides with the chlorine monoxide, the 2 oxygen atoms bond to form an oxygen molecule. The chlorine atom is thus released and is free again, free to destroy another ozone molecule. This ozone loss sequence is called a catalytic cycle and is a natural process that has always existed in the stratosphere. As a result, 1 chlorine atom may destroy hundreds of thousands of ozone molecules before it forms one of other chlorine compounds and exits the stratosphere.
The level of ozone in the stratosphere is balanced between the production of ozone due to the highly energetic UV radiation and the loss of ozone by catalytic processes. This delicate balance has been upset by a 5-fold increase of chlorine in the stratosphere since the early 1970s, causing the balance to shift to lower ozone levels. The chlorine increase has resulted from the chlorofluorocarbons, or CFCs, released in large amounts due to human industrial activity. Unlike ozone, CFCs do not break down easily. They are not water-soluble like most chlorine-containing compounds, which may be washed out of the atmosphere by rain. In fact, CFCs eventually are transported intact into the stratosphere, where their concentrations have been measured by NASA instruments.
In the upper stratosphere, the CFCs are broken apart by UV radiation, the first step in a chemical process that destroys ozone. The chlorine atoms are then freed from the CFC, and they can catalytically destroy ozone. Ozone depletion is occurring because the CFCs and other manufactured compounds are causing additional ozone destruction.
Originally, the ozone depletion process was based on theories. However, British scientists studying Antarctic ozone and NASA scientists gathering data from an ozone monitoring instrument in space were stunned in 1985 when they discovered that ozone had decreased dramatically over an area near the South Pole. We called this ozone decline and loss the ozone hole. Ozone depletion has occurred in both hemispheres of the world. Many countries contributed to the problem. Fortunately, most industrial nations have signed agreements to phase out many of the damaging chemicals. Meanwhile, the thinning of our protective ozone layer is a reality, and it adds to the basic danger of excessive exposure to the sun.
Okay, so after watching the two videos, let's do a quick summary for what we have learned today. So the first thing you have learned is the reaction of alkanes, in particularly your free radical substitution mechanism, whereby you talk about your initiation, your propagation, and your termination. Do remember that you need to have the arrows, draw the arrows. You also talk about the environmental consequence of the use of alkanes. You also talk about the catalytic removal of selected exhaust gas. And lastly is the enhanced greenhouse effect that you have watched through the video. And the last video is about ozone. So, yep, that's all for our alkane lecture.
That's all, folks.
Thank you.